All right, we're going to start in earnest now talking about data exploration and data visualization. This is going to be not super technical, or at least not math heavy. Near the end, I'm going to be talking about the grammar of graphics, and I will introduce ggplot2, which is the package in R that allows you to make nice professional charts. I'm just going to show you the at least talk about the basics of ggplot2. Part of your job, and that project will be to use, if you decide to use R in ggplot2, will be to expand your understanding of ggplot2 so that you can produce charts that are substantially more appealing to the eye than the base charts that R can produce, or base charts that Python can produce through matplotlib. And so we're going to focus here on the concepts and the notions that underlie effective data exploration and effective data visualization. This is actually a super important aspect of the data analysis process. Up until very recently, data problems were mostly of an engineering nature. You had to design a machine, and you wanted to make sure you design a machine that would do what it was supposed to do without breaking down, or it was a scientific problem. Namely, you were trying to formulate theories, and you wanted to know if the data or if experiments would support your theories. And we solve problem either empirically, collection of data, the scientific method, theoretically, using first principles, so deducing possible consequences, so trying to prove statements based on what we knew to be true, and again using logical means of deduction or inference, or potentially through the use of computation. Like you might have collected some data and you would like to come up, or at least you used data to derive quantities, computations that could support your position or help you build better machines. So that's the way we did things up until, very recently. The data that we had often contained additional information which was ignored. So we weren't using all of the data that was available to us, or potentially some of the data had characteristics that would make it clear that something is a little fishy, but we weren't usually digging into auxiliary or extraneous features to try to make sense of our data. Now, there's one important factor. I'm going to focus on the scientist element here, but this is also true for the engineers. You would set up experiment as a scientist to try to validate your theories. Well, one of the issues about setting up experiments is that they are expensive. The Centre Européen de Recherche Nucléaire, CERN, which was for years like the biggest physics lab where they would run these particle accelerators to try to study particle physics, it can cost upwards of like hundreds of thousands of dollars to run one run of experiments, right? So these things were very expensive, so you couldn't run too many experiments, which means that ultimately we had very few data points to work with. At least very few data points were generated by the experiments, relatively speaking. In the 21st century, at least since the advent of digital data collection, well, things have changed. There is a lot more data, like a lot more data. Most of the data is digital. Back when Kepler was using observations of the planets to try to deduce the shape of the orbits, There wasn't computers. There weren't computers. You couldn't digitalize the information. It was painstakingly recorded and placed on in ledgers and books. But now a lot of the data that we collect is just stored on the cloud. It's stored in a digital format. And one big difference in the way we interact with data is that for the most part nowadays, data is observed as opposed to generated by an experiment which has been specifically designed to test various tenets, if you want, of a theory, or to test how a machine works. Now, you'll see a lot of statisticians nowadays have a real bone to pick with data analysis and data science in general. I suspect that the underlying reason why that's the case is because data is not collected through a designed experiment. It's because we literally go out and observe it. And when we observe the data, there are various types of biases that can enter into the process that might make it so that the experiment, if you want, or the collected data isn't representative anymore. There's too many issues with biases. So nowadays, when we look at, we still do design of experiment. It's not the case that nobody else does this anymore. StatScan, for instance, whenever they run a national survey or a provincial survey or wherever it is that they survey things, well, they set up their experiment by coming up with a sampling plan, a sampling design, and then you can make general inferences about the population as a whole from a small, hopefully representative sample of the full data set. But their response rates are abysmal. Apart from the census, which is a mandatory survey for Canadian citizens to participate in. I think that might also be true for permanent residents. I'm not sure, but that's a mandate. It's not a sample anymore. It's really a full census. Apart from the census, if they get like a 10% response rate on surveys, they're ecstatic, right? So nowadays, a lot of StatScan work, for instance, will supplement their data sources by including voluntary responses, right? So undesigned experiments. Send out a tweet, let people know that they can answer a questionnaire and they will collect data this way. But by moving into this area where you collect data without a sampling plan or an experimental plan, you move away from guaranteed inference to a larger population into the realm of data science, where presumably there you hope that the volume of data you collect will make up for the fact that you do not have a designed experiment. Well, why am I harping on this? Why am I taking the time to talk about this? It's because nowadays we have a fourth way to solve problems, right? A way which isn't as scientifically sturdy, if you want, as design of experiments would be, and that is the usage of data visualization and data exploration. But that's a big conceptual shift. It actually changes the way we approach data. We can still do all of the technical things we could do on data before, or at least we could also say that we could also have done these things before. But now, the fact that we have these waves of data coming in and that they're not designed, not generated by experiment, sort of changes the way we report on these things. It makes the discipline substantially less solid, sound. When we announce results of analyses based on a data set, very often the only thing that we can really say is that Well, this applies to a situation where the underlying character of the data is similar to the one we had in our data set. We can't always then use that data unless it's a census data set to expand or to apply to a larger population. And that's fundamentally a shift in the way we view data. So it's not just about the collection and the processing according to specific designs. We need to focus a lot on data management, data analysis, and data visualization in the reporting side of things. You've worked with data before, presumably. Some of you might have data jobs outside of school. If that's the case, you're aware that the picture that we usually present in a classroom setting isn't really what happens in the reality. Like ideally, we set up this sort of like analytical method, which is meant to be fairly linear. You set up your objective, which will help you design your infrastructure and data management, and at the same time inform your data collection process. In the old days, this is the part where you come up with a sampling design, a sampling plan. Once you've collected the data, you prepare it, process it using the infrastructure as well, and then you will spend some time exploring the data. You've explored the data, you understand the data, then you switch to modeling and analysis. Pretty easy, straightforward. You do the modeling and the analysis, and then you take the results of your analyses and you, well, transform them into useful chunks, useful results. And once that's done, you just go out and communicate your results. Pretty straightforward. Well, this linear process here is not at all the way that data analysis works. In practice, what usually happens is you might not even have set up an objective or a rationale to start with. You might just have a big data set and you're trying to figure out what you can get out of the data set. Right? So very often you don't even start with the objective and the rationale. Then you'll eventually move on to setting up the infrastructure and data management. But in practice, it's often the case that your infrastructure dictates the kind of data that you can collect, which in turn dictate the kind of question, the kind of objective you might have about the data set. And so these three pieces go hand in hand, and you iterate through them, and it's not clear that one of them is the main driver. Eventually, you might end up with some data, and you'll start preparing it. You'll start processing it, doing a bit of cleaning, getting rid of observations that are duplicates, for instance, or imputing missing values. And as you go through this process, you might realize that, hang on a bit, I keep on getting duplicate entries. Why is that the case? Well, perhaps you didn't set up your infrastructure properly, and so you'll go back and change the infrastructure, or perhaps your data collection process has bugs in it, which makes it so that a lot of values are not being recorded, and so you usually end up having to go back to previous steps in the process. That's true as well for data exploration, data modeling, data analysis, and how you use it. Very often, until the very last step of communicating the results, writing the report, writing the paper, sending a dashboard, or sending a link to a dashboard to your boss or to your stakeholders, you have to go back and potentially go back more than one step to finish clear the process. the thing is, even after communication, if you realize that there's a problem with the analysis, or with the data collection, or with the infrastructure, you still have to go back and presumably produce new reports, new dashboards, new policies based on these modified analyses. It's not a one and done process in the real world. And that takes a little bit of getting used to, I think. Now I've forgotten what it felt like to first encounter the reality of a data project in the classroom as opposed to a data project in a real life or real work setting. It's been too long for me to remember what it felt like, but I do remember being shocked, like severely shocked, and realizing that what I thought I would be able to do because I had this data set wasn't really going to be useful because a lot of conditions hadn't been met along the way, and then we had to go back and change things. We're going to talk about the data exploration part and the communication part. This is where visualization mostly comes in. It also comes in modeling and analysis, but that's not where what I want to focus on right now. So roughly speaking, I'll talk about data exploration briefly, how you use data visualization prior to analysis, how you use it after analysis. I'll show you a little visualization catalog, the types of things you can produce visualization-wise. Then some very good visualizations, the Hall of Fame, some very poor visualizations, the Hall of Shame, and you will see that it's not obvious sometimes which ones are in the Hall of Fame and which ones are in the Hall of Shame. You need to spend some time exploring the visualization to see whether it's a good one or not. And that's dangerous because some visualizations might look like great visualizations, useful visualizations, but upon further review they are not. And they may have fooled a fair number of people into thinking that they were a good visualization. And that feeling sticks. Like, people don't usually come back to take a second or third look at the visualization to decide whether it was a good one or a bad one. So it's very easy to lie with data. It's even easier to lie with charts. Then we'll talk about the grammar of graphics. That's ggplot2. So if you're already familiar with ggplot2, that's great. I'm going to provide you with, roughly speaking, about a lecture or half a lecture of content there. There's also reports and R notebooks on the website where I do about 40 to 50 examples at various levels of coming up with data visualizations in R. So you can use those as your baseline on which to work for the project. And I'll spend a bit of time telling you about dashboards as well. I'm not a big dashboard person. I prefer to focus on the individual visualizations, but of course, once you've created visualizations, you can also make them interactive, and you can stitch them together into a dashboard that will allow you to tell a bigger, larger, more comprehensive story of the situation that you're studying. Okay, so most of this, what we're going to do in the first 3 or 4 lectures, I don't actually know how long this is going to take. Presumably 3 or 4, no, not more than 4 lectures, I can tell you that much, but up to about 4 lectures. It's going to be not very technical. Okay, but it is by far the most important part of the course. If you were to take away only one thing from the course when you enter the work world, the job world, it would be that data visualization is super, super important. Right? Without good data visualization, it doesn't really matter what else you do in the work world. The analyses, no matter how clever you are, will not be read or taken seriously if you cannot draw the attention of stakeholders. right? If you cannot make people believe the story you're telling, well, they won't believe your story. They won't be interested in what you have to sell as a story. So that part, to me, is crucial. And it is very often overlooked. Now, obviously, some of you may have done some visualization before, and so nothing that I'm going to say here invalidates what you might have done previously visualization-wise, but it's just the type of thing that we need to keep in the back of our minds if we want to be able to use our skills as quantitative people properly. Interesting. Okay. I mean, I have, just as an aside, so I've worked with some of you previously on projects, and the very recent project that I'm thinking of, it is not at all obvious that you need to get very, very, very deep into analytical territory to please your clients, to give them what they want and what they need. Surprisingly enough, being able to come up with, 30, 40 charts from which they can build a narrative that explains the situation, and they wouldn't use 30, 40 charts to build the narrative. They might use 8 to 10 charts, but that can actually go a very long way to help them meet their goals, right? And it's perhaps surprising to those of you who worked on these projects with me that it's not the analysis part that really blew them out of the water. It's the exploration part and the visualization part. Let's start talking about data exploration. There are basic questions you need to ask about the situation, right? Data is never just data. It doesn't live in a vacuum. Data doesn't exist for real without context. If you just have a bunch of bits of bytes on the cloud, you can't really make sense of it. I mean, even if you could run analyses or algorithms on them and get results, that's sterile, that's austere, that's not something that can help you. In fact, it's quite dangerous to run analyses without having a good contextual understanding of the situation. There was a recent case, I forget which university it was in the States, I think it might have been Northwestern, but perhaps that's not the university that I mean, where they asked two physicists to build a model to predict the number of COVID cases they would have on campus based on various scenarios. And so the physicists built an epidemiology model. In fact, they found that the model was easy to build, and they managed to do a little, do a little dig at epidemiologists along the way, just letting them know that they don't think that their discipline is very difficult and it's easy. The university administration swallowed the model hook, line, and sinker, decided that it's safe for us to reopen the campus. So classes were being offered in person instead of online. And sure enough, the cases ballooned way up. And it turns out that actually not understanding epidemiology and COVID as a whole, and more importantly, actual student social behavior, doesn't matter how clever you are, doesn't matter how great your data is, if you use it without the right contextual understanding, your model's going to be super crappy. In fact, the reliance on this model proved to be problematic for the university and for whoever ended up getting infected that shouldn't have been infected if the university had not opened its doors. Right? So it's very easy as quantitative technical people to say, I work with data all the time, I can make sense of the data, trust me. I mean, that is a dangerous, dangerous, dangerous path to follow, especially if you're going to be working with social situations and social data that comes from people as opposed to scientific experiments. People are difficult to understand, and whenever we're dealing with people, we have either conscious or unconscious biases that make it so that we can't really deal with data as just data. We need to try to have a good understanding of the system that the data represents. Right? And that's an also fairly difficult thing to do, understanding the system. The data that we have at best is an approximation of the system that we're trying to understand, that we're trying to model. When we're making a model to try to understand the spread of a disease like COVID-19, we make a lot of simplification assumptions. I don't know if you're familiar with epidemiological models. If you're not, Dr. Burkett here offers some, and Dr. Smith as well, some pretty cool classes on epidemiology and biostatistics in general, so you might want to take these courses and get a better understanding of how it works. But if you're familiar with these things, often people will use the so-called SIR models. So these tend to be systems of differential equations that look at the relationships between the suspected people in your population, susceptible people in your population, susceptible to be infected, the people who are infected, the I, and the R means the people who've recovered from the infection. And then there's networks that tell you what percentage of specific people that are susceptible will be infected if they enter or if they contact people that are infected, and so forth and so forth. So, I mean, some of these models can actually be fairly complicated. You know, you have multiple ways to be infected, and then sometimes there's a relapse. If you've recovered, you can catch the disease again, and so forth. So some of these models are pretty complicated from a modeling perspective, but even the most complicated of these models is only going to be an approximation of an underlying system, right? The disease, when it spreads, doesn't really care about differential equations. It just spreads, right? And whenever you have a stochastic component to these things, a probabilistic component, who knows if you've captured the right probability distribution to explain what's actually happening, right? So we make assumptions. We'll often say, it's roughly speaking normal, or it's roughly speaking a Poisson distribution, or what have you. Well, that's dangerous as well, right? So it's an approximation of a system, and the system itself tends to be an approximation, at least the conceptual system that you've come up with tends to be an approximation of the true situation. Because the true situation, as I think it was Isaac Asimov, the science fiction writer, once said, the only true model of the universe is the universe as a whole. So every time you try to make a model of a subset of the universe, you are, by necessity, ignoring a huge amount of interactions and links. You're trying to reduce it to a small component which is tractable, on which you can work. Well, you make a simplification assumption there. And then whenever you have this small model and you collect data for that small model, you are again making simplification assumptions. So you lose a lot of information along the way. It's like compressing a file. Sometimes you will lose important information. So do you understand the system that your data represents? I mean, do you understand? And if you say yes, well, you don't really understand, but you understand the system. Now, if you're still here listening, as opposed to having put this on mute and just disappeared for a while, you might be wondering, why am I harping on this? Why am I focusing on this thing? Why did I just spend 10 minutes talking to you about the fact that data is always going to be an approximation of the system, which is itself an approximation of the universe as a whole, or the situation of interest as a whole? Because people make decisions on the basis of data and the analysis, as though it was not just an approximation, as though the data was the situation. And that's not the case ever. Right? The only time when the data is the situation is when the data is when your analysis can only speak about the data set that you have. Right? But typically people don't just want to talk about the data set. They want to use the data as a stand-in for something else so that the analysis that they conduct on the data set can be used to make predictions or inferences or to help support or inform policy decisions with the data and the analysis. So that can be very, 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 very dangerous. You need to be careful. Other questions you might need to ask about your data set prior to starting the exploration proper. How does it represent the system? What is the data model? What's the link between the measurements and the components of our system approximation to the situation as a whole? That's a very difficult question to answer. We'd probably spend a full course just talking about representing systems with data. I won't, but this is something we could do. Who made the data set? Who collected it? When was it collected? For what purpose? You'd like to think that data doesn't lie, but data lies. Sometimes it lies because of negligence. Sometimes it lies by design. You need to try to have a handle on what we would call the metadata about the data set, information about how it was collected. If you have a flat file, and in this course, and in most courses you will take in the Math and Stats department, data comes in flat files. It comes in CSV files, or text files, or Excel spreadsheets, rows and columns. For Math and Stats people, that makes sense because we think of data, roughly speaking, as a matrix. And we think of data as a matrix because we have a lot of linear algebra that tells us how to work with matrices. And we have multivariable calculus that tells us how to deal with continuous matrices, so to speak. In the real world, not every data set contains only numerical values, so it's not really a matrix. It would be more something that we would call a data frame. Do you understand what the rows in your flat files represent? Do you understand what the columns represent? Because in the real world, not only is it the case that data comes in data frames, not matrices, it usually comes in databases. We don't usually have data available to us as a flat file, as a CSV file. We need to build a flat file from the various data sources or data tables in our database. Do you actually understand what the flat file is meant to represent? Do you have enough information as a whole to answer these questions? Do you, for the contextual understanding, for the representation of the system? And if you don't have enough information, where can you find more information? One of the challenges that we have, one of the issues that we have, is that we're a bit stupid or blind when it comes to our data set. If we do not have enough information to answer these questions, we don't typically know that we don't have enough information to answer these questions. Right? Because we don't usually think about this part of the process. We treat data as an actual object that has everything we might possibly want, and that is basically a holy grail, an always right object, something to look up as some platonic ideal of truth. Well, data is not any of these things. You do not have to jump to visualizations right away. There is nothing wrong with using tables, summaries, to get a first sense of a data set. If I give you this summary of a data set, can you figure out how many variables I have in my data set, how many observations I have in my data set, what the variables are, what this data set is about? Are you able, just by looking at this summary, to say something about this data set? Does anybody want to give that a try? Smith, are you still there?
Yeah, I'm here.
I'm going to put you on the spot, bud.
I'm sorry, what was the question again?
You weren't listening. I know you weren't listening. None of you were listening. Why am I even doing this? I'm kidding, of course. Take a look at this summary here that you see on the slides. And I'm asking you if you can, just by looking at the summary, answer some of the questions about this situation, the system, the data. Is it easy to tell how many variables there are, how many observations there are, what the variables represent, or potentially what the data set is meant to represent?
No.
No, you can't.
I'd say no.
Okay.
No.
Can you tell how many variables you have? Is this something that you'd be able to do?
No, I don't think so.
Well, you can tell how many you can mute it now, it's good. You can tell how many variables there are in this summary, and you see 4 variables. There's a variable called CL, a variable called NO3, a variable called NH4, and a variable called season. Right? Is that it? We don't know. All we see here is information about 4 variables. There could be 4 variables in this data set. There could be a lot more than 4 variables. You can say a little something about numerical versus categorical values. It looks as though these first 3 variables are numerical in nature, right? We have what's typically called a 5-point summary, although there's 1, 2, 3, 4, 5, 6, 7 measurements or metrics about the summary, but we have the minimum value, first quartile, the mean or the median, centrality measures, the third quartile, the max value, and some NAs here. So this summary allows us to figure out, okay, we have some data quality issues. Some of these variables are missing. I have a bit of a picture, if you want, of the full distribution. And so I'm seeing that all of these values are positive here, or at least non-negative. So I'm measuring quantities which are not going to be negative. I'm measuring positive quantities. All right, so that's something I can get from the summary alone. I get that this is a season here, seems to be a categorical variable, and it looks as though, because I recognize autumn, spring, summer, and winter as names of seasons, that there might be 80 observations in the autumn, 84 in the spring, 86 in the summer, 90 in the winter. I was like, all right, so I'm getting that overall there seems to be a total of, well, 340 observations, roughly speaking, spread out equally amongst the seasons. What else can I say? If I was to make draw a little diagram of the CL and the NO3 variable, I would probably see that it looks like there's outliers here. 391 and 45, these are pretty big values compared to the rest of the distribution, especially the third quantile, sorry. NH4 also has, look, there's a jump of 2 orders of magnitude here. 24,064 is a measurement for one of those things. Like, okay, so that seems a little weird. Possibly, although I don't know if that's the case or not, just by looking at the summary, possibly this could have been 240.64. Perhaps the comma is meant to be right here and there was a data entry error. It's a possibility. That would at least remove the existence of this observation here, which is 2 orders of magnitude greater than 75% of the data. So okay, I can play this game without any contextual understanding. And unless you've taken a course with me before, you've never seen this data set or this table. This is usually the data set that I trot out for my data cleaning exercises. So some of you have seen this data set before, and you might know what it's supposed to represent. But those of you who haven't, you'll look at this and you say, I have no clue what this is supposed to be about. Like, what are you talking about? Why couldn't it be the case that the largest value for NH4 could be 2 orders of magnitude greater than 75% of the observation? Right? If you don't have contextual understanding, there's only so many things you can do with tables of numbers. Granted, without contextual understanding, there's also so many things you can do, or only so many things you can do with data visualizations as well. Now, what about the names of these variables? CL, NO3, NH4. Do these mean anything to anyone? Like, I don't want to start, like, picking people at random. So at first, I'm going to ask somebody here to volunteer some information, or at least volunteer a thought. Does anybody want to hazard a guess as to what CL, NO3, NH4 might represent?
Just like chemical compounds?
Yeah, they sound like chemical compounds, right? Yeah, chemical, sure. It's like, all right, chlorine, Cl, NO3. Do you know which one that is? Without looking it up, it's hard to tell. But you're not completely blind here. How would you look up what NO3 is supposed to be? Well, you go online, and perhaps you would just Google something like NO3. And you can't see this because I'm not sharing my screen, but so what is NO3? And NO3 is nitrate something. It's a series of nitrates. Okay, so nitrate is a thing. It's a chemical compound. What about NH4? That's ammonia. Ammonia. Okay, so now I'm getting a sense that these are compounds that are usually found. Well, where? How do I? So I'd have to start looking at these things a little bit more. Now, where do you get that information? You might have a chemist at your disposal. If you're part of a team, you will have potentially non-data people who can answer these questions for you. If not, you need to find the information yourself. So when I'm talking about initiative as part of my multiple eyes framework, where you'll be graded on, this information might not be given to you directly. You need to try to find a way to get it. Even if in the occurrence, the prof isn't guiding you by the hand saying, well, what is NH4? Where would you find this information? As it happens, I'm going to stop the game now. I'll just tell you what this is meant to be so that you can move on to the next step. These represent a subsample or subset of the measurements that were taken of 340 European rivers. And we've measured the chlorine, NO3, NH4, as well as a bunch of other things that are not included here. pH, there's some oxygen content, some monoxide content as well, and so forth. You couldn't possibly guess that from the summary of the data. There is just not enough information here to really help us figure out what this data set is about. And this is what I mean when I say that without contextual understanding. I mean, you can run analyses here. You can probably come up with a model that would verify if there's a correlation, or at least some sort of an effect between the season and the Cl, NO3, and NH4 levels. You could do that. But without really understanding what it's meant to be about, your results would be very dry, unapplicable. You're missing a crucial component, understanding the context. How do we use visualizations before we start the analysis? By that I mean before we start the traditional analyses, regression modeling, clustering, classification, any sort of typical thing you might have learned in other courses, machine learning or not, right? Well, there's four reasons why you might want to do data visualization before you run analyses. They can help you in the data cleaning, data processing stage. Right? Data visualization might help you identify a variety of anomalous entries, either because you have invalid entries or missing values or potentially outliers or even influential data points. It's a little bit less obvious how you would deal with influential data points, but that's a possibility, right? You can also use them to shape your data transformations. If you've done some regression before, if you've taken regression analysis, you might remember that in order to be able to use a general linear model, come up with the relationship between the response variable and the predictors, there's like 5 assumptions that need to be met. Something about the independence of the errors, residuals, the linearity itself of the response with respect to the predictors. I don't know how to pronounce this word in English. Homeoscedasticity, which is roughly speaking the idea that your predictor measurements have some uncertainty in them as well. They're not like true, honest-to-goodness, exact measurements. You typically need to have an assumption of constant variance throughout, so that the variance of your error doesn't change depending on where you are in the predictor space. And that's not often the case. Like, it's very difficult, or you have to be very lucky to get a data set where this actually happens from the get-go. More often than not, you need to transform either your response or your predictors in order to be able to check all of the hypotheses assumptions. Well, which transformation do you use? There's tons of transformations out there. Data visualization prior to analysis might actually inform your choice of data transformations, give you a more efficient way to find the transformations. You don't need to try everything randomly, because the visualization might tell you, one of these 2 or 3 methods might actually be good methods to use. Right, so binning, standardization, normalizations, any of the various transformations like Box-Cox that allows you to find the right powers to use for your predictors or your responses. If you're going to use something like a PCA, Principal Component Analysis Transformation, this is all something you can get a sense of through data visualization. I said get a sense of. Another thing that you can do prior to analysis is to help you get a sense for the data. That exercise that we played with the table and the algae blooms data set, like the various chemicals in the rivers, well, it's much easier to get to the point where we got if we use visualizations as well as tables. Right? So this exploratory analysis, which is crucial, and most of us don't really focus on. We're technical people. We want technical results. We don't want to think or talk about these very qualitative components of the data. because that's not really something we can measure. But often these are the chunks that people respond to emotionally. And finally, you can use them to help identify hidden data structures. If there are clusters in your data, it's conceivable that you will want to run various analyses or different analyses on each of the clusters, as opposed to just using one analytical method for the data set as a whole. But how are you going to know if there are clusters unless you visualize and try to find clusters beforehand? So these patterns that you find that are hidden in the data, the structure that you did not know was there at first. Some data exploration through visualization might help you identify them, and that can actually help you plan your analysis component better. It's important, right? Again, part of the initiative, you need to establish an analysis plan, which will be specific to the data and situation that you're working with. So now we've talked about intuition, trying to get a sense for the data and the context. An initiative, two of the I's, to help us, that can be helped with the help of data visualization. Or that can be achieved, if you want, or semi-achieved with the help of data visualization. I'll give you a few examples of what I mean here. What can you get out of this? So this is a chart which measures the arrival rates at various counters. So the arrival rate is given horizontally and the service rate vertically. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 counters in total. And this is the relationship between the arrival rates and the service rates. And it looks as though, based on this alone, if you were to try to, describe this chart in one word, give me a label or description of what this chart is showing, you might conclude that, well, the more people arrive, so the higher the arrival rate, the higher the service rate. Does that make sense to you? Can you imagine situations where, when something is very busy, like let's say you're at a bank, for instance. That's a bad example because we don't do banks anymore. Perhaps let's say you go to a restaurant and there's a large number of people coming in waiting to be served or waiting to be seated. The speed at which they get seated increases. Is this usually what happens? The more people arrive, the faster they're being served? Anyone? Is this your experience with waiting? It does depend on the place. You're right, Oliver, sorry. It depends on, what it is that you're waiting for. This is actually waiting times, not at a restaurant, but these are waiting times at various, you're right. If it's exactly grocery store, you increase the number of cashiers. This is roughly speaking what happens here. These are airports, or at least checkpoints at airports. The more people are waiting to be scanned or to get their luggage scanned and their person scanned, the faster people are reacting. If you're seeing that nobody's around, nobody's waiting, you might be somewhat lackadaisical in your work. I'm not saying there's not that much of a difference here. The service rate is only increasing by a little bit. But if you're seeing that there's a lot of people waiting and perhaps they need to get to the plane on time, you might actually speed up your process. This is roughly speaking what's happening. So we get a bit of a structure here. We get the idea that there's a relationship between the speed at which people arrive and the speed at which they're being served. So this is good. If you just showed me a table here with the pairs, arrival rates and service rates, I probably wouldn't have been able to see that right away. 11 points, that's too many points for my brain to really make sense of it. Another thing you might notice is that there's one point here which doesn't seem to fall or follow the pattern. Do you see this point as well? So now I've told you that these represent airports. They happen to represent Canadian airports. If you have an understanding of the Canadian context, do you think you could guess which airport this would be? Anybody? Can you think of one airport in the country which is unlike the other airports? Anyone? Has anyone?
Probably like the private one in Toronto. I forgot what it's called.
Billy Bishop, it could have been.
Billy Bishop,
Billy Bishop Airport. As it happens, you're right, this is a Toronto airport. I wasn't fully forthcoming here with you. This isn't just quite the customer arrivals at counter. It is being also sliced by the number of open checkpoints. And so what's hidden here is that there are a lot of checkpoints open for this airport. And so this is really the arrival per checkpoint, or the rate per checkpoint. In reality, this is Pearson Airport, right? Even though it's only 0.8 customers arriving at a specific, per minute per checkpoint at Pearson. There's just so many more checkpoints at Pearson on average that are open that it's just bringing down the information. So if you know that this is meant to represent like the big Canadian airport, at least the airport that is unlike the other one in Pearson, well, this sort of makes sense that this point here doesn't seem to follow the same pattern. So a visualization easily allows us to see that one of those is unlike the others. Right? Now, I could be wrong about this being because Pearson is different. Okay, it's just a guess I'm making based on my understanding of the context. The Toronto airports, Canadian airports, I've been to most of them. My understanding of Canada, my understanding of what's busy and not busy, my understanding of people working faster when they see bigger lines because they want to help people not miss their planes. None of this is given by the visualization or the data. This is all outside contextual understanding. Unless you are completely different, completely unlike all of the other classes of students I've worked with, like at this point, if you're still even paying attention, you're probably thinking to yourself, why are we still talking about this? Give me something real to work with. This is a stupid data set with 11 observations and 2 variables. You're spending way too much time talking about such a small potato visualization. But this approach, what I'm trying to show you here, at least, is what it is that I want you to do or think about when you're working on your first project. I want you to try to get an intuition, a sense for the data set. This is what I really, really, really want students to do here. Let's take another example. Oh, sorry. Let's talk about something else. The importance of multivariate visualizations. Visualization sounds great in theory. In practice, we are limited by the fact that we typically visualize things on a flat surface, whether it be a sheet of paper or a computer screen. We only have these 2 dimensions to work with. Now, from your mathematical studies, this basically is represented by R2, the plane. And R2 only has room for 2 dimensions. And so at best, you might think that this is the only thing you can ever hope to produce, these 2-dimensional charts. In practice, we have discovered or developed tools over the years that allow us to plot more than 2 variables at the same time on the same chart. You can represent, as I said, two of your variables by positions on the plane. That's good. But you can also use characteristics of the markers to represent other variables. You can use the size of your marker to represent something else. One thing I could have done in the previous chart here was to represent the observation, the X, by a bigger X if it was a busier airport, and a smaller X if it was a non-busy airport. And then you would have right away seen a gigantic X here because Pearson is so busy. You can use colors, different colors, to represent different variables. You can use a value. You can literally add a number to a marker that represents another thing. Or potentially one of the things you've already represented could be twice represented, both by the size and the actual number. That's a possibility. You can use texture as well, how you decide to fill the marker. Is it going to be solid filling? Is there going to be horizontal or diagonal or vertical lines like back in the old Macintosh days? You can decide a line orientation. You can decide your markers align and either points this way or points this way. You can use the shape. You can have squares. You can have circles. You can have triangles. You can have X's and crosses. You can have, there's a lot of little shapes you can use here, diamonds. You can also use motion. Right? You can have these interactive displays that show you what happens over time when time passes, and so you can come up with movements. In theory, then, you have access to, the two physical, the two position variables plus size. So, position 1, position 2, size, color, value, that's 5, texture, line orientation, shape, that's 8, motion, that's 9. So you could represent up to 9 variables on a 2-dimensional chart. And that's about the limit of what we can really do here from a geometrical perspective. We don't have that much to work with. I need to warn you, though, that 9 is way too much. Our brains, no, that is so split. It doesn't make sense to use all 9 at all. Our brains are not really wired to look at a chart and see 9 competing things at the same time. It is going to be too noisy. In the real world, when we're out and about doing stuff, driving, or back in the old days, like hunting or other things, it would have made sense. I mean, we can take in more than 9 inputs simultaneously, but we take in these 9 inputs in a very non-attentive manner. Like, we don't know that we're taking in all these inputs together. If we sit down and try to parse a chart, try to read a chart, try to understand what the chart is saying, so we're focusing, we're being attentive, it's very difficult for us to really make sense of much more than 4 or 5 variables at the same time. Okay, 6. Sometimes you can get away with 6. You can try it. So one of the things I'm going to suggest you do in your project, I mean, if you wanted to show initiative, for instance, or innovations, like, let me try stuff other than what he's at. I'm going to try to come up with a visualization that uses as many variables as possible. And perhaps you can explain why these visualizations aren't really useful, aren't really given us much. Don't just take my word for it. Try it. Try to come up with competing elements, having so many variables on your chart that you can tell the whole picture at once. Are you able to draw insights? Another one of the I's. Are we able to draw insights from these overly complex charts? Right, now there are some exceptions here. I said that you can only place 2 variables, or at least you can only represent 2 variables with the position on a flat chart. There are some exceptions. We're going to talk a little bit about scatter plot matrices, which in theory allow you to look at pairs of variables, and you can look at all the pairs of variables. So if you have n features, n variables, well, you'll have sorry, n times n plus 1 divided by 2 visualizations that you can put there. So you can literally view all n variables together in terms of their pairs, paired interactions. That's limited. I mean, you don't get the full picture. You just basically get two-dimensional slices throughout, but that still allows you to view all variables at the same time. There's also something called parallel coordinates, which can be used to plot all of your variables vertically, parallelly speaking, and then you join them with lines. And so an observation is a curve, not an actual point. And if you have 50 variables, then you can come up with 50 axes, and each point would be a line going through 50 axes. We'll talk about these later as well. So yes, all of this is feasible, but you get to the point if you have too many variables in your scatter plot matrix or too many axes in your parallel coordinates plots, you can't make sense of them anymore. You cannot parse much more than 7 or 8, potentially 9. So it turns out that even though there are methods that allow you to plot more than 2 variables using position, they don't actually work for what you want them to do. If you have too many variables, everything looks like a big jumble of lines. If you have too many variables, your scatter plot matrices, when you try to render them on the screen, they will just look like little blank dots where all the observations overlap one another, and you can't draw any insights from it. Yes, the numerical factor. So there's a question here by Xiaolang. What if the additional factor is numerical? It cannot be depicted by color or size. It can be. I mean, you can come up with gradient scales. You could say, for instance, that if the value is 0, for instance, the color will be black, and if it goes to the maximum of, let's say, 200, it will be blue, and then you build a gradient between black and blue so that any of these values go into or get mapped to a gradient color. All right, now we'll talk about using colors down the way in a little bit as well. You got to be careful with colors, not only because a fair percentage of the population is colorblind, but because it's actually quite difficult to read gradients that have too many colors in them. Right? But the intensity, the intensity can be used to represent various numerical values. Same thing with the size. You can literally say, like, my numerical variable represents the radius of the bubble that I'm using. And so values that are bigger get to be very big, and values that are smaller shrink continuously to a point. There is a problem there, which we'll talk about again later. If you use area as a measure for the quantity, our brains aren't very good at working with areas. So it's very hard for me to tell the difference between a circle whose area is 10 and a circle whose area is 5. I can tell that one is larger than the other, but I can't tell by how much it is larger. Right? It's very hard for me to say 2 circles and say the area of that circle is twice as big as the area of that circle without an actual label where the value of the quantity is written, which is why sometimes we do add a label, an actual numerical value added to the marker. Very good question, Xiao. Take a look at this representation of the original dataset. Now, I didn't talk at all about the dataset that was on the previous slide, and perhaps some of you wondered what it is that you were looking at. Let's go back for a sec. You're looking at basically, nothing. I mean, there's a name here. This is a NASA data set using one of the spaceships that they have, CM1. And we see a bunch of points, and it looks as though the points are mostly aggregated in the bottom left. And there's a few outliers here and there, a few cloudy observations. But nobody can make sense of that, right? I mean, it's just 2 variables, 2 axes. I didn't even tell you what the axes were. There's no contextual understanding here. See how we can improve this chart with the use of, what we call chart elements or design elements. right? So here I can add or plot together 5 variables. I have the horizontal position and the vertical position. So horizontal position is the time per line of code. So it's a measure basically of how difficult it was to write a specific computer or code component for the spaceship. So time per line of code, if it's very high, it's because it took me a while to write each line on average. Presumably because it was more difficult to come up with the right line of code. Vertically, I had something called the cyclicity. I'm not going to explain to you what that is. It's a computer science concept. There's at least there's one point here which has the a very high cyclicity. So these are 2 variables represented by position. Forgive me. Drink of water. Then I have the shape, which in this case is categorical. A circle tells me that there were no defect in the code component, and a square tells me that the code component was defective in some way. What we're noticing right off the bat is that when the time per line of code gets to be very high, presumably because we're writing a crucial component, and we want to make sure we don't make a mistake, because we spend more time to write it per line of code, well, we see here that these that took a lot of time to write, there were no defects in them. That's not completely surprising, right? At least it sort of makes sense with our understanding of writing code, if we've ever written code. What else do we have? We see that there seems to be a lot of defective pieces in the small area here. There seems to be an equal preponderance of defective and non-defective components. You can't really tell because it's not obvious here, but a lot of these overlap. So behind the squares you see some circles. You can sort of see them because I made them not completely solid. They're somewhat transparent, and you can see some circles underneath. So there's a fair number of points here. This looks to be, roughly speaking, somewhat equal distribution of defective and non-defective. Although it seems that if you go up this way, there are more non-defective, and if you go to the right this way, it seems to be a preponderance of defective components. Okay, sure. The size of the marker tells us something about the size of the component, the number of lines. Oliver, I'll respond to this question in 1 second. So what we're seeing is that, okay, so there's one big component here which proved to be defective. Again, perhaps not completely surprising that defective components tend to be larger in general, although there's a fair number of small defective components as well. We don't see a very big non-defective component. The more lines of code that you have, the more opportunity there is to have a mistake or a defect in one of them. Right? So that sort of makes sense as well. And then there's something called the intelligence per line of code. I'm not defining what that is, but it goes from blue to green for the not defective part, and from yellow to orange for the defective parts. And since we don't know what intelligence per line of code is, it's a little hard to really sort of parse this. All in all, though, I think you will agree, even if you don't really know anything about the data set and the context, it is easier to parse the chart here than it is to parse the chart here. Nobody can gain any insight from this black and white 2-dimensional chart. It's a little bit easier to say something interesting about this chart. Now, don't get me wrong, it is a boring chart no matter how you swing it, even if you spruce it up with more components. To answer the question that Oliver is asking, are the squares made to be superimposed on the circles? No, they're not. I've made this chart. This is a chart I made myself. I made it with ggplot2. And we will talk about ggplot2. This is the last thing I'm going to say, then we're going to stop and meet again next Wednesday. But ggplot2 is the R package, as I said, that allows you to make decent, nice charts. And it's very neat. It works with something called the tidyverse. Tidyverse is a sort of new, well, it's not new, a new approach, but an interesting, very commonly used approach now to data analysis, and a lot of things are compatible with ggplot2. And one of the drawbacks of ggplot2 is that if you want to do something which the RStudio team doesn't think you should do from an aesthetic perspective, you can't. So it is impossible right now in ggplot2 to plot a family of circles, a family of squares, and to have a different color scale, color gradient for the two groups here. As it currently stands in ggplot2, if I want to use it without modifications, I can produce circles and squares, but I can only produce circles of, circles and squares in one of the gradients. I can also only produce circles and squares of the same shape. It's impossible to mix the scale of the circle and the scale of the squares. So what I actually ended up doing to produce this chart, I had to produce a circle chart first, then a square chart with a different tool, an image processing tool. I put these two things together.